And welcome back as we go ahead and continue to look at our sorting algorithms. Previously we had looked at merge sort. Now let's go ahead and dive in to go ahead and take a look at its companion algorithm, quicksort. So with quicksort, one of the things that we take a look at with our definitions here of how this algorithm works is that we have our split definition much more sophisticated, whereas before it was our join when we looked at merge sort. Now, how this works is that we have an arbitrary value in the array, which is chosen, and then this value is what we call our splitting value. In a realization that we actually look at with our code, we'll choose a begin as whatever our splitting value is, but really any value in that array will work equally just as well. Now, the elements of the array are rearranged so that all those elements are either less than or equal to the splitting value at the front of the array, and all the values that are greater than the splitting value are at the other end of the array. And the splitting value is placed so it divides the entire array into these smaller and larger elements. So once it's done splitting them, let's look at sorting them, right? You'll note that the small elements, though when we do this, are not sorted, and the larger elements are not sorted, but all the elements before the splitting value are smaller than any of the elements after the splitting value. The small elements are sorted using a recursive call. The larger elements are sorted by another recursive call. And then these two sorted segments are just combined with the join method. In this case, our join method is as simple as could be. It pretty much does nothing. Because the sorted small elements all precede the larger elements, the entire array is already sorted. So that kind of begs a question here. And when we start looking at our code, do you actually need that second array? With both the merge sort and the quick sort, these things can be done without the use of a second temporary array, which we had called temp in our code. However, the detail of this is really a distraction if you want to think of the message we're trying to talk about here with this example. In a real application, you may or may not, depending on the details, want to consider the possibility of doing some kind of sort realization without the use of a temporary array. Now, there are restrictions we do have to discuss on our sorting patterns. The sorting pattern, like all patterns that we have discussed, or you can look at in the future, has some restrictions upon where it applies. So if we think about how we formulated the sorting pattern, it only applies to types for which the less than operator is defined. Also, it only applies to sorting into increasing order. It does not apply to sorting into decreasing order. If we wanted to do a decreasing order, we'd have to do some rework at how our algorithm is. However, all this that we talk about, of course, is just a result of us simplifying details in order to make presentation clear. You can make the pattern much more general by, for example, replacing the less than operator with a Boolean value method called compare, which has two arguments of the base type of the array, so such as string, which returns true or false depending on whether or not first comes before second. Then, if we think about it that way, the only restriction that the compare method must have is a reasonable definition for how it's going to operate. So, before we kind of wrap up here with our patterns, there's one more thing I want to discuss, which is the efficiency of the sorting patterns themselves. Essentially, any sorting algorithm can be realized with this kind of sorting pattern that we've talked about. However, the most efficient implementations are for those with the split method divides the array into two substantial sized chunks, such as half and half, or 1/4 and 3/4. A realization of a split that divides the array into one or very few elements and the rest of the array will not be as efficient. The merge sort realization of split divides that array into two roughly equal parts, and the merge sort is, of course, indeed very efficient. It can be shown, though we're not going to worry about it here, that a merge sort actually has a worst case runtime that is best possible up to a certain order of magnitude. Our quicksort, by comparison, also is going to divide our array into two portions that might be almost or equal or might be different in size depending on the choice of a splitting value. If you split it at the very first element, for example, and then all the rest of the array, well, that's probably not going to be very efficient, right? So that's going to get you some extremely unfortunate cases where the split might be very uneven. In the worst case, runtime for a quicksort is not as fast as that of a merge sort. However, what ends up happening in practice is that the quicksort actually can turn out to be a very good sorting algorithm and is usually preferable to merge sort just because it's an easier implementation in some manners. Selection sort, which we have looked at all the way back in our first programming 1 world, divides our array also into two pieces with a single element and one with the rest of the array interval. Because though a selection sort has a kind of uneven addition, selection sort has a very poor runtime. Although it does have the virtue of simplicity. There's no recursion involved when you're using selection sort. And so if we look at the big O notation here for these common sorting algorithms, let's start first with the very simplest one that we first learned about, which was bubble sort. Bubble sort, of course, is big O of n squared. And you can see n squared is a pretty steep curve. It grows very quickly. Obviously, there are algorithms that are worse, but n squared is still very steep here. Well, what about selection sort? Selection sort, we test out, does have sometimes some slight advantage over bubble sort. Bubble sort's biggest strength is it's very simple. So you need to test something real quick, then use the bubble sort. Well, selection sort, unfortunately, has a very similar runtime to bubble sort. So even though it might be slightly more efficient in certain circumstances, it's not guaranteed. And if you look at the worst case, remember this is a worst case scenario, selection sort is going to be just on the same path as bubble sort. Well, what about our friend merge sort? Well, merge sort is actually big O of n log n, and you can see that one actually will plateau out. It's not in here, but big O n log n is right in here, in between here, and so it's actually going to plateau out. It's not going to have this sharp curve like you see with selection or bubble sort. And what about quicksort? Well, quicksort is going to also share the big O of n log n. Now, there is a small caveat with that because we said that's the practical definition, but the worst case, which is very rare, is big O of n squared, which means it would share very much with bubble and selection sort. But again, remember, in most practical cases, it's going to operate much more on big O of n log n. And again, let's go ahead and take a look at our code just to see how these algorithms are being used. So if I go ahead and pop behind the hood here and take a look at how the quicksort is operating, you can see we have our sort, which is, of course, using just the exact same approach as what we're used to seeing. We have our split here, which is the much more complicated method here than what we saw with our merge sort. And if we look at our join, it's a nothing to do because it doesn't need to do anything. So let's just go ahead and pop back to our quicksort, give that a quick run, and you can see we are getting those array contents. Actually, again, I'm going to tab these in here just so we can see these a little bit nicer here. So we're going to run that one more time. And again, we get the same thing as what we saw before. We have here a unsorted array, so 7.5, 5.5, 11.0, 3.0, 16.0, 4.4, 20.0, 14.0, 13.0, and 42.0. And then, of course, we sort them using our quicksort algorithm. And again, these function very similar. However, what's the biggest difference between this and the other one is that trade-off. Before we said, we want to trade off a simple split call and have a much more complex join call. But here we said, we're willing to do the complexity in the split, and in exchange, our join call is very simple. You can see there's nothing to do, because remember, a lot of that sorting is actually happening here with our quicksort, depending on where we're staying, where that split point is going to be defined.